Imagine another civilization is searching for Earth right now. They've found our sun. They've pointed their telescopes toward our planet. Maybe they've even sent us a message. And we may never know. Not because they failed to find us, not because our telescopes aren't powerful enough, but because the universe itself makes two civilizations finding each other astonishingly unlikely. Distance, time, signal, survival. Each one is another wall standing between us. So, if intelligent life really is out there, why may we never find it? It seems like this should be a numbers game. Our galaxy holds somewhere between 100 and 400 billion stars, and a meaningful share of them carry planets sitting in the temperate zone, the kind of place where liquid water could exist. Estimates put that number in the billions, just within the Milky Way. Billions of candidates. That should be enough. But watch what happens the moment you add a single requirement. Many scientists think long-term habitability may depend on factors like a stable atmosphere, a star that doesn't flare too often, and a magnetic field strong enough to hold that atmosphere in place across billions of years. We don't know exactly which conditions are essential and which aren't. What we do know is that each condition you add doesn't subtract a few planets from the list, it narrows the list considerably. By the time you stack every likely requirement that separates a habitable rock from an actual civilization, the number we started with barely matters anymore. Billions shrinks dramatically, and a smaller pool is exactly the kind of number distance can swallow whole. And suppose one of those survivors really is out there, orbiting a stable star with a breathable atmosphere. Confirming a planet's location is one thing. Confirming that anything is actually breathing on it is another. Oxygen showing up in a distant atmosphere can come from a living biosphere, or it can come from ordinary chemical reactions with no biology involved at all. Telling the two apart from light years away, using nothing but the color of starlight filtered through an atmosphere we will never visit, pushes the evidence into a gray zone that no current instrument can fully resolve. We could be staring directly at a living world and still walk away unsure. And that's the next wall, because even if a few of those survivors made it through every filter and became something capable of reaching out, they would immediately run into a problem that has nothing to do with biology at all. Maybe you think distance is just a matter of patience. Wait long enough, and eventually a message crosses the gap. Here's the correction. Nothing, not a signal, not a spacecraft, moves faster than the speed of light. Our nearest possible neighboring star system, Proxima Centauri, sits at a distance that stretches past ordinary comprehension, 40 trillion kilometers, or roughly 4.24 light years. That's the closest star to our own, and a signal sent from there still takes over 4 years to arrive. Now stretch that same math across the galaxy. The Milky Way spans a distance that dwarfs anything we can intuitively picture, 946 quadrillion kilometers, or about 100,000 light years from edge to edge. A message sent from one side takes 100,000 years just to cross, one direction, assuming nothing weakens it along the way. So even a civilization, sitting a few hundred light years off, isn't someone you talk to. It's someone whose message left before human writing existed, and whose reply, if they sent one at all, wouldn't arrive until long after everyone alive today is gone. And that estimate assumes a clean, uninterrupted path. In practice, a signal traveling for tens of thousands of years has to cross regions thick with interstellar dust and gas, the same material that blocks much of our own view toward the galactic center. Some of that material absorbs radio energy outright. Some of it bends and scatters a signal just enough to smear a clean transmission into something closer to background static long before it reaches us. That alone would be enough to explain the silence. But suppose for a moment that distance wasn't the obstacle. Suppose a message could somehow arrive instantly, undistorted. There's still something else standing in the way. Something that has nothing to do with how far the signal has to travel. It feels like the fix is simple. Keep listening. Long enough, and surely two civilizations will eventually overlap. Except overlap isn't about patience either. It's about a window, and the window is brutally short. Earth has existed for about 4.5 billion years. We've only been leaking detectable signals into space for a little over a century. On a 4.5 billion year timeline, that's a sliver so thin it barely counts as a moment. Now assume another civilization rises somewhere else in the galaxy. Nothing guarantees their broadcasting phase lasts long either. A civilization might only produce detectable signals for a few hundred years before it destroys itself, loses interest, or simply moves past the kind of technology that leaks into space at all. Nobody actually knows how long that window tends to last, because we have exactly one data point to study, our own, and our own story isn't finished yet. Estimates for how long a technological civilization might stay both active and detectable range from a few decades to tens of thousands of years, and the real number could sit anywhere across that entire span. A guess spread that wide barely narrows the odds at all. Picture two lighthouses on opposite sides of an ocean the size of a galaxy, each one lit for a few seconds, once, somewhere across 4.5 billion years. For either one to see the other's flash, both beams need to be lit at the same narrow moment, roughly aimed the same direction, close enough that the light hasn't already faded into nothing. This isn't only theoretical. In 1977, a radio telescope in Ohio recorded a single, powerful burst of unexplained signal lasting just over a minute before it vanished, never repeating despite decades of astronomers pointing instruments back at the same patch of sky. Whatever produced it, natural or otherwise, the window to confirm it closed the moment it ended. If a genuine transmission behaves the same way, arriving once and never again, we may only ever get one chance to notice it, with no guarantee we'd even be listening at that exact moment. That isn't a technology problem. No telescope fixes a mismatch that already happened millions of years before we existed to notice it, and say, somehow, against all of that, the timing does align. There's still one more filter standing between a signal being sent and a signal actually being caught. A signal that survives the distance and beats the timing still has to reach us intact, and every step from here on strips something else away. It weakens the farther it travels, the same way a shout fades before it reaches the end of a street. It has to rise above the static of stars, pulsars, and background radiation that fills the same frequencies we'd need to search. It has to land inside the narrow slice of the sky and the narrow band of frequencies we actually happen to be scanning at that exact moment, out of a search space large enough that our efforts so far have covered a fraction too small to matter. There's also the matter of aim. A deliberate signal, the kind built to be noticed, usually has to be pointed at a specific target to carry any real strength by the time it arrives. Broadcast it in every direction at once, and the energy spreads so thin across the sky that almost none of it survives the trip in a detectable form. Point it precisely at us instead. and whoever sent it needs to already know exactly where we are and when to aim, which assumes they already solved the same distance and timing problem we're only just working through now. Distance wasn't enough to stop it. Timing wasn't enough either. The signal still has one final test to pass, and this one has nothing to do with where or when it was sent. It can still arrive too faint to separate from noise, aimed at a patch of sky nobody was watching, on a frequency nobody was listening to. Perfect timing does nothing if the message dissolves before it reaches an open ear. There's another possibility hiding underneath all of this. We assume a signal, if one exists, would look like ours, a burst of radio waves crossing the dark. But a civilization further along than us might have moved past radio decades or centuries into their own development, communicating instead with lasers, tightly focused particle beams, or methods we haven't built an instrument capable of noticing yet. Searching only for radio is like scanning a single shelf inside a library the size of a continent and concluding the rest of the building must be empty. And if space itself isn't the reason for the silence, if distance and timing and signal strength could somehow all be solved at once, there's a deeper possibility waiting underneath all of it. Maybe the silence doesn't start out here in the gap between stars. Maybe it starts back at the beginning, before a signal was ever sent at all. This is the idea known as the Great Filter. Every wall we've crossed so far assumes a civilization survives long enough to reach it. That assumption might be the weakest link of all. Somewhere between simple chemistry and a civilization capable of reaching across the stars, there may be a bottleneck so severe that almost nothing gets through it. Maybe that filter sits behind us. Maybe the leap from basic chemistry to living cells is so unlikely that it almost never happens, which would make Earth the rare exception rather than the rule. Or maybe the filter is still ahead of us. Maybe civilizations reliably reach our stage of development, and then, more often than not, fail to survive it. Resource collapse, self-inflicted catastrophe, technology outpacing the judgment needed to control it. History gives at least one uncomfortable data point for that second version. Humanity built the technology to end its own civilization within a few decades of building the technology to search for another one. Nuclear arsenals, climate instability, and the slow strain on the infrastructure we rely on to keep listening all sit on the same short timeline as our brief broadcasting window. If most civilizations face a similar narrow stretch, where their reach outpaces their ability to manage it safely, the period during which they're both alive and detectable could be far shorter than most estimates assume. Either version lands on the same place, a galaxy that could easily contain other minds, spaced too far apart, timed too narrowly, filtered too aggressively for any two of them to ever line up long enough to notice each other exist. So here's the real answer. Underneath every layer we just walked through, the problem was never really whether life exists somewhere else. Across billions of candidate worlds, statistics suggest it's plausible, maybe even likely. The real obstacle is that existing and being found are two different achievements, separated by distance measured in tens of thousands of years, by timing windows measured in centuries against a backdrop of billions of years, and by a filter that may quietly remove most civilizations before they ever get the chance to be noticed at all. None of these walls needed to conspire against us. They simply exist independently, stacked on top of each other by nothing more coordinated than physics and time. And stacking is enough. The universe may not be silent because nobody is out there. It may be silent because space and time may prevent civilizations from ever becoming each other's contemporaries. And if that's true, every civilization scattered across this galaxy could spend the entirety of its existence searching, listening, sending signals into the dark, without ever realizing it was never alone.